Okay, you can see the statement of the problem. We're to find the intervals, and we're talking about x values, for which the graph of f of x equal 1/4 times x cubed minus 3x is increasing and where it is decreasing. I need to say out loud here that the point of this is to do this analytically and not to worry about trying to look at a graph and use a calculator. That's the whole point. We want to make this decision without seeing the graph. So you can expect that on the test that pertains to this, a calculator is not going to be allowed, so don't get used to it today. Now, here's what we need to do. Here's the steps. And as we go through them, I'll remind you why. Step one in this case is to find f prime of x. Because what we're after is to find out where f prime of x is positive, that's where we're increasing, and where f prime of x is negative, that's where we're decreasing. So in this case, it's pretty easy to calculate the derivative of f prime of x. What would we do? We'd say, take the exponent 3 and multiply it with 1/4, so we'd get 3/4, and then we'd decrease the power by 1, so we'd get 3/4 x squared, and then minus the derivative of 3x, which would just be 3. Okay. So that's easily done. Sometimes that takes several more steps if we have a more complicated function. In this case, it was fairly straightforward. Now, step 2 is to find the critical numbers. Find the critical numbers of the derivative. Okay. Now, let me remind you of why. Is the critical numbers are the places where we can change from increasing to decreasing or vice versa. So let me write down what the critical numbers are, and then I'll remind you of why that's important. The critical numbers are the x values, or are the values of x for which either f prime of x is equal to 0 or f prime of x is undefined. That's what the critical numbers are. And again, the significance of this is the graph can only change directions at critical numbers. I want to say one more thing here before we move on to this. It says, read what that says, and pay attention to that again. The graph can only change directions at critical numbers. It does not say that the graph will change. Okay, it does not say that. So be aware of it. This does not say the graph will change directions. It just says if it's going to change directions, it's only at critical numbers that can happen. In fact, we'll see examples in a bit where it doesn't change direction at critical numbers, but it never will change directions anywhere else. Okay. So that's the reason we're going through this, is that's going to help us find the boundary where it changes directions. Okay, well, let's get back to what we were doing. That is, we need to find the critical numbers of the derivative. And remember, the critical numbers are where the derivative is 0. So if we're asking this question, if the derivative is 0 and above we calculated the derivative, as 3/4 x squared minus 3, we want to know what x values make that true. Well, I tell you what I would do is we need to solve this equation, and I recognize it as a quadratic equation because of the x squared, but I don't like the fractions. So I'm going to multiply both sides by 4. And that's going to let me get rid of that fraction 3/4, isn't it? So I'm multiplying both sides by 4. And on the left side, when I multiply 4 with the 3/4, I get 3. So it becomes 3x squared, and then minus 4 times 3 is 12. And on the right side, 4 times 0 is just 0. So now it looks like a more normal quadratic equation. Now this is a quadratic equation where x to the first power is missing. And so we don't have to factor or use the quadratic formula here, which we may in some other cases. Remember, what we usually try to do here is we separate the x squared from the constants. That is, we'd add 12 to both sides, and then we'd divide on both sides by 3. So we get it down to just x squared is equal to a number, and that number is 4. Well, okay, that number being 4, well, if x squared is 4, then x is plus or minus the square root of 4, which means specifically x is either plus or minus 2. Now, the other possibility, see, remember, critical numbers are the values of x for which the derivative is either equal to 0 or the derivative is undefined. Now, when we come over here and we look at the derivative once again, is it ever undefined? Is it undefined ever? Well, remember what the derivative is. It's 3/4 x squared minus 3. And although we might get some strange numbers, any x is okay. So it's never undefined. Okay? So the only critical numbers we have are related to when the derivative is 0. So two critical numbers. Two critical numbers. X equal 2 and x equal negative 2. Okay, well, here's what we do next. Let's finish this on the next page. What we end up doing, it's the next step, okay? And I guess we could call it we're kind of beginning step 3. That's what we're doing. We draw a number line, and this is more or less related to an x-axis. Remember, we saw those numbers where we changed directions on the x-axis, an A and a B and a C and so on. Well, we found the critical numbers 2 and negative 2, and those are the places that we might change directions. Might. Only place it can, but it's only might. And so what we do is we find these positions, these are the critical numbers, and we plot them on the number line in the appropriate order. So negative 2 is first, and then positive 2. That's the order, so we lay them out like they are. Remember, those came from as the critical numbers of the derivatives. Now, here's what we're going to do next. What we want to know is that when x is less than negative 2, is the derivative positive or negative? And when x is between negative 2 and positive 2, is the derivative positive or negative? Because remember, the derivative is going to tell us whether we're increasing or decreasing, and it's at negative 2 and positive 2, the only place that can change. So we more or less build a table. Okay, so that's kind of to get us started there, the way we were thinking. But here's really where I am now. I'm going to kind of do this in more of a table form now, if you can imagine. Now, this is exactly where, I'll do it this way. This is where x is equal to 2, and this is where x is equal to negative 2. And so on the left of 2 would be negative infinity to to negative 2. So this part, and we're talking about this out here, see, that's what we're talking about. And of course, in between negative 2 and positive 2, we're talking about here. And so that's the interval from negative 2 to positive 2. So that's what we're talking about here. And then out here, of course, we're talking about these values that are bigger than 2. So that would be 2 to infinity. So I basically have 3 intervals represented here, don't I? Now what we're going to do is we're going to test the derivative. We're going to test f prime. And what we're testing for is taking a number that's in this first interval between negative infinity and negative 2. For instance, x equal negative 10 would be one such value. So what we do is that we take that value and we plug that value into the derivative. Okay? Now, what was the derivative? Let's see, the derivative, remember, f prime of x was 3/4 x squared minus 3. So we're calculating f prime of negative 10. Well, that means we put a negative 10 in the place of x, and we end up getting 3/4 times 100 minus 3. And 3/4 times 100 is 75. So we get 75 minus 3, or 72. Now, what's really significant here, see, f prime of negative 10 is 72, which means the slope of the tangent line, when x is negative 10, the slope of the tangent line is 72. That's real steep, but mostly what's important is that it's positive. That's what we're really after. So in this case, the slope is positive. Now, the significance there, if you remember, okay, the significance there is that whenever the slope is positive, that tells us something about the graph of the function. That tells us about the graph of f. When the slope is positive, the graph is increasing. So we know in the interval between negative infinity and negative 2, the graph is increasing. Okay, well, let's go further. We need to test a value that is in this interval between negative 2 and positive 2. So a value that would fit that category would be x equals 0. So what do? We put the 0 into the derivative. We can do that down here. F prime of 0, well, that's 3/4 times 0 squared minus 3. That's 0 minus 3, or negative 3. So this tells us that when x is equal to 0, the slope of the tangent line is negative 3. But mostly, the slope is negative. And so that tells us that the tangent line is going down. Hence, the graph is going down. So when we find the derivative is negative in here, now we know the function is decreasing on this interval. And see, we know that the function is decreasing all the way through that interval because it can only change at negative 2 and positive 2. So between negative 2 and positive 2, it has to be either increasing or it has to be decreasing. It can't be some of both. So one test point is enough. Okay, well, let's go to the next value, the next interval. We need a test point. So we could use x equal 10 again, or we could use x equal 100, okay? Or we could use x equal 3 or 2.5. I'm going to use x equal positive 10. But when we come down here and we calculate f prime of 10, remember we're testing the derivative to find out the slope of the tangent line. We have 3/4 times 10 squared minus 3, and that will be just like above. We'll end up with a 72. And I don't really care that it's a 72, except that says it's real steep. I care that it's positive. So we know f prime of positive 10 is positive. And if our slopes are positives, that means that the graph is increasing. And once again, it has to be always increasing or always decreasing in an interval. Because at 2 and negative 2, the only places it can change. So when we're between 2 and infinity, it can't change. It's one or the other. That's, again, one reason we just need to test one value. So now we've concluded, okay, we've concluded that f is increasing on two different intervals. It's increasing here, and it's increasing here. That is, it's increasing on this interval, and it's increasing on this interval. So that's on the interval from negative infinity to negative 2, and from 2 to infinity. And we also know that f is decreasing. That's where the derivative is negative, isn't it? It's decreasing on the interval between negative 2 and positive 2. And so we've answered the question without even looking at a graph.
Well, sorry for that mix-up there. You can see a little goof up. But what I've done here is I've shown the graph of the function that we were just analyzing. And remember, as we discussed in this, that the value right here, the critical number negative 2 and the critical number positive 2, those are the two critical numbers. Whoops, another goof up. Hold on just a moment, please. Well, here we go again. I apologize for the interruption. I've marked the two critical numbers, the x values negative 2 and positive 2, to make the point that below we saw that we said that the function was decreasing on the interval from negative to infinity to negative 2. So that's all these x values. And it was also increasing on the interval from positive 2 to infinity, so that's these x values. And we can see that that corresponds, of course, to this part of the graph where we're increasing, and also to this part of the graph where we're increasing. And we did that without ever looking at a graph. And then you can see between negative 2 and positive 2, of course, the function is decreasing, and we also determined that without ever looking at the graph. So this derivative is a very powerful tool that lets us analyze a graph before we even know what a graph looks like. Let me pause here and we'll go to the next problem. So please bear with me.
Okay, as we continue our discussion about finding the intervals for which a function is increasing or decreasing, we see the problem stated here. As it says, find the intervals for which the function f of x equal x cubed minus 3x squared plus 3x is increasing and for which it is decreasing. So more quickly through this now, we know that the first step that we need to take is to find f prime of x. Okay, oops, we need to find this. Okay, that's step number 1, find the derivative. Well, if we can find the derivative, it's a polynomial, it's going to be pretty easy. What will we get? 3x squared minus 6x plus 3, won't we? So we found the derivative, done. The next thing we need to do is find the critical numbers. Okay, find the critical numbers. Now remember, the critical numbers are x values, and they're the x values of the only places we can have a change in direction. That's why they're called critical numbers. And the critical numbers are what? They're the x values for which the derivative is 0 or for which the derivative is undefined. Now, the derivative is a polynomial, okay? Say the derivative is a polynomial here. And a polynomial is defined for all values of x, so this doesn't apply in this problem. So what we're looking for is to find out when the derivative is 0. And so the derivative being 3x squared minus 6x plus 3, we want to know when that's 0. Well, that means we're solving an equation. Okay, and when we solve this equation, I'm noticing that there's a common factor of 3 through all of this, so I can factor out a 3 and have 3 times x squared minus 2x plus 1 is equal to 0. Now, people have been shown different things, but let me tell you what I would do here real quickly. I would just divide both sides by 3. Since that 3 is a common factor in the numerator, when I divide by 3, that's going to go away, isn't it? but I've got to divide the other side by 3. And on the left side, that simply leaves x squared minus 2x plus 1, and on the right side, 0. So we have an easier function to deal with. Okay, now, what do we do next? We need to solve the equation, and we'll do that by factoring, I think. We'll try to factor this left side. Let's see, an x times an x will give us our x squared, and we have a positive right there, which means the two signs down here have to be the same. But since this is a negative, both of these signs have to be a negative. I mean, the only way we get a positive is positive times positive or negative times negative. And it's got to be negative times negative because we have a negative in that middle term. Now, the only choices of getting 1 are 1 times 1. And so now we just check and make sure that our guess is right. And of course, x times x is x squared, and x times negative 1 is a negative x, and another negative 1 times x, another negative x, and so on and so forth. It is factored correctly. Now, in this case, when we solve, of course, then we get x equal 1 as the solution, and that's the same with each factor, don't we? We'd set those factors to 0, but the only solution is x equal 1. So this time we have 1 critical number. Last time we had 2, didn't we? We just have 1 critical number here. So if it's ever going to change directions, it changes when x is 1, and it can only do that next one time. So our next job, or the next part of this, is that we test intervals that this x equal 1 creates. Test intervals, and when I say test, we're testing the positiveness or negativeness of the derivative. Okay, so kind of set up for our table. Maybe overdid it. This is where x is equal to 1. So here is negative infinity up to positive 1. And on the other side is from 1 to infinity. So what we're doing here, of course, is we're going to test. We need a test point. So I'm maybe going to test something like 0 is in that interval, isn't it? So I need to test the derivative when x is 0. Remember, that's what we're doing here. We're considering f prime of x. And so when x is 0, what do? We need to calculate. Now let me reiterate. F prime of x, we found, is 3x squared minus 6x plus 3. And so we're testing the 0 value in the derivative. And when we do, you can see, don't you, that we'll end up with just a positive 3, because all this other stuff ends up being 0. So we get a positive 3. Now the issue is that for this test point, the derivative is positive. The 3 isn't so important, it's positive. Well, okay, then the conclusion we're bringing to bear here is about the graph of the function. Say we get some information. The graph of f tells us that if the derivative is positive, the graph is increasing. So that's what's going on down. That's what we're understanding. Okay. Well, now we need to test in this interval. And so we need to find out an x value that's in there. Well, we can use a large x value, or we could use a small one. I'm going to use x equal 10. That's certainly in that interval. And so what we want to know is, for that x value, are we getting a positive or negative derivative? So we simply put 10 into the derivative. So that would be 3 times 10 squared minus 6 times 10 plus 3. And of course, 10 squared is 100, and 3 times that's 300, and then minus 60, and then plus 3. And I don't really need to, again, I don't really need to calculate that number. I need to notice that I can tell that it's positive. And so that was what was important here, is that it was positive. So what we know is the derivative is positive for that x value. Okay, well, if it's positive, then that tells us that the graph is increasing, doesn't it? This is important. I know I keep saying it. But x equal 1 being the only critical number is the only x value for which at which the graph can change directions. And since it's increasing on the left side of 1 and it's also increasing on the right side of 1, then it's always got to be increasing, doesn't it? Okay? And so what we could answer now is that f is increasing for all values. It's increasing on the interval from negative infinity to infinity because it's increasing to the left of 1 and to the right of 1. So that's the way we would actually answer this. It's never decreasing, is it? It's never decreasing. Well, of course, we could graph things and notice this in advance, but what we're trying to do, once again, is make these decisions based on our analysis and not based on a graph. But what I would like to do before we leave this problem is show you the graph and show you why this makes sense when we see the graph.
Well, here you can see the graph as promised, and you can see that this function is continually going up. It levels off slightly. It doesn't ever get flat. And of course, if we expanded that more, we could tell that it never does get flat. But it is important to notice that this position right here is the critical number. Whoops, well, here we go again with this problem I'm having. There's the critical number, x equal 1. And what we found at that critical number is that's what we tested for. Remember, on the left of 1, we tested to see whether the derivative was positive or negative. That tells us that in this case, the tangent lines all had positive slopes, and that meant the function was increasing. And then on the other side of 1, we tested the derivative and found out that we got a positive result, which meant it was increasing on the other side. It was this critical number of 1 was where the derivative was actually 0. And what that corresponds to is a tangent line. I'm not drawing a very straight line there. I apologize for that. But the tangent line at that point, if it has a slope of 0, if the derivative is 0, that means the tangent line at that point has a slope of 0. So it's a horizontal slope. So we can have a situation where that slope of 0 doesn't mean that we have a peak or a valley. It means we have something that looks like this. So once again, what we're showing, and the issue here is the critical numbers are where it can change direction, the only places that it can. But the critical numbers don't mean that it does change directions there, as we see in this problem. Well, that's the end of this part. We'll look at some other problems in the next part, and we'll get to that right away.